Alright, this is on simple machines, and you'll want to make sure that you go to the website that was linked in Google Classroom. So you're going to see the simple machines, and you'll see that there are 6 different simple machines, and I'm going to kind of go over a little bit of them in detail, but I just want to highlight a few things on the website. So as you're looking to get some information, remember that the ideal machine, okay, is that the energy that we put into it is equal to the energy that we get out of it, and energy is really just work. Okay, so we've been talking a lot about work, and so really it's a force times a distance is equal to a force times a distance. And I think that was at the end of our video from our last notes. So we're going to kind of go through some of the details of each of these machines. You can kind of go ahead and click on each of the machines to get the further detail, but I'm going to switch over so that the screen is, or the computer screen isn't showing anymore, but now we're just going to go straight into me being able to write. Alright, so here we go. Let's first talk about, I think the easiest simple machine to first look at is just the incline. So I'm going to draw a little picture here of an incline ramp. And we've looked at ramps already in this class. So when we look at how this ramp is being used, we're going to start with our object down here at the bottom, and we're going to push on the object this way. So we're going to apply a force through the distance of the incline. Now, the reality is why are we using this? Well, we're using this so that we can get the box from this point here down here on the ground to this point up here. So really, the force that we would need to lift as an output force is going to be our force of gravity, because we're just lifting it up, and then we're moving it through this distance. So when we go back to the premise here that energy is equal in all machines, the work that we put into the machine has to be equal to the work that we get out of the machine, which means that the force that we put into the machine times the distance that that force is being applied is equal to the force that we get out of the machine times the distance that we get out of the machine. So now we just look at this and start to identify a couple of things. So like if I look here, what my output goal was to lift this box up this height. So really my output force is just the force of gravity on that object. The distance that we're really moving this is what we would call the height of this ramp. So it's the height of the ramp. The input force is going to be what we're going to push with. So that's an applied force. And then that input distance is going to be whatever the length of that ramp is. So really when we start to identify how we deal with this simple machine, we want to look at it in terms of the length of the ramp, and the height of the ramp, the applied force, and the force of gravity. Now if I kind of look at what happens here, we can split this up. I'm going to put my forces on either side. So really I'm going to do my applied force. I'm going to ratio it with my force of gravity. And I'm going to ratio my height and my length. Oh, hold on. I want to reverse that. I'm going to put the length on this side. So length over the height equals the force of gravity over the force applied. And there's a reason why I switched that around. So when I look at this, I know that this number is going to be bigger and this number is going to be smaller. So when I make my ratio, I'm going to make a ratio that's going to be a number bigger than 1 for our ramp. Now this is what we call the IMA, the ideal mechanical advantage. So the ideal mechanical advantage for this incline is going to be, I'm just going to check it. There you go. For this incline is going to be the length of the ramp divided by the height. And if this is bigger than 1, then we are going to see what we like to call a force advantage. So it's going to give us a force advantage. Now let's look at what happens here on the force side. what that means is this number is going to have to be the bigger number. This number is going to have to be the smaller number. So we're going to put less force into this than what we would need if we just lifted it straight up. And that's the reason why we're using this ramp. It doesn't save us any energy. So the energy in and the energy out is the same. What it saves us is we got away with less force. Now we had to apply that force through a bigger distance. So we're actually at what I call a distance disadvantage. So this would be a distance disadvantage. So force is at an advantage, distance is not. So we see that as not an advantage in that case. And that's kind of what happens with the incline. Now, the reality is this incline plane, if we were to look at it in terms of a free body diagram, so I'm going to switch back here. So here's my box. I know that I'm going to have a force of gravity that's acting down. The ramp itself is going to force normal force on it. We're going to apply a force in this direction, so we're going to have that applied force, and then there's going to be a friction force. So when we look at what happens here, the force of gravity gets split up into its two pieces like we've talked before, so this being that force perpendicular to the surface, and this is that force parallel to the surface. So the parallel force and the force of friction are really being balanced by that applied force if we're moving it at a constant speed. Now what that means is, it means that we're putting extra force in due to the friction that's involved, more than what we would have to. So if like this was a frictionless surface, if the mu of this was equal to 0, then there wouldn't be any friction force, and the amount of applied force would be identical to the force parallel, which puts us in an ideal situation, so that would give us like an easy way to do our math. The problem is that when we have the real life, where maybe our friction is going to be like 0.5, okay, for a coefficient of friction, that means that friction force is adding force to what we'd have to do. Now this is called efficiency, okay? So we see this as an efficiency loss. So friction is taking away some of this. What this really looks like over here is that the work in is bigger than the work out. So like this is a fixed value. You can't change that because we want to lift this box up this high. But now we're putting in more because of that friction force that's there. So really when we look at this, the work out over the work in is causing this to give us a loss in efficiency. So this is going to give us a number that's less than 1. So some kind of a percent loss. Okay? And this is a loss in efficiency. So we see that as kind of a loss in our system, which means that we actually used more energy whenever there's friction involved because we have to overcome that friction. And that's going to be a common theme as we start to look at some of these other machines. Now, to kind of keep along the same line as what we're looking at here with the incline, I want to kind of look at two others that are very similar to this. Okay, the two that we're looking at would be our screw, which when we think about how a screw is formed, it's like taking an inclined plane and turning it around like a spiral staircase. Okay? And what happens is we get this effect where there's this gap, and we call that the pitch. And that pitch represents similar to the height of an incline. It's proportional. And then we look at the distance that it takes to go around. That's like a circumference. And that circumference represents kind of the length. So really, when we look at the ideal mechanical advantage of a screw, it's going to be that pitch okay, or the circumference, divided by that pitch. And I don't remember what letter they used for pitch. I'm just going to write pitch. Okay, so we can see that in most of those cases, again, this number will be bigger than this number, so we'll have an IMA that'll be bigger than 1, which means that we're going to be at a force advantage. Distance is not going to be at an advantage for us. So high amounts of friction involved here. And really that's something that we expect out of screws, because we don't want the screws to slide themselves back. So we're looking at increasing that friction force here. So we want mu to be a really big number so that our screw doesn't actually back itself out. Now the other one that is similar to this would be our wedge. So like I'm going to look at a wedge. This would be like a knife blade or an axe head. When we look at this, we're applying that force downward. So this is our applied force. And what we're really trying to do is push the force out. Okay? So the force that we're going out is going to go along this length here. That's called like the width of the wedge. And then the applied force is really going through the length of the wedge. So we usually look at it in terms of the length of the wedge over the width of the wedge. Okay? And that's going to give us our IMA that'll be bigger than 1 again, so that we are at an advantage of force. Okay? Now, when we that's how we kind of look at these three machines. So again, highly, I should say, a very low level of efficiency. They're all going to give us some issues, and that's the way we kind of set those up. I'm going to pause right here because I need to switch over, and we'll talk about the other three machines. All right, the next group of simple machines that we want to talk about is going to start here with a lever. Levers are basically beams that we are going to apply some kind of a fulcrum to. Now, we can adjust where we want this fulcrum to be. So this is something that can move this way or this way. And then what we do is we usually put like the load on one side. So again, we're going to look at the box that we're going to put on one side, and then how much force we're going to put on the other side. So this could be our force applied. And then we're going to lift up this. So in other words, we're back to thinking about it like an F of G. Like how much weight are we going to have to lift? Now, when we move this box, okay, we're really kind of trying to move this end of the lever. So there's a distance that's associated with this motion. Okay, and then there's a distance that's associated with this motion. This would be our distance in versus our distance out. Now what happens is these distances are proportional to the length that we are away from our pivot point. So these are proportional to those lengths. So when we start to talk about this, we look at this in terms of the length of our effort, okay, versus the length of our resistance. So when we set this up and we start to think about this in terms of an IMA, we usually look at it and say, well, the IMA is going to be equal to the length of that effort arm, okay, that's that distance in that we're going to move this way, versus the length of our resistance arm, that's the distance that we move this way. So we have some ways that we can kind of shift things here. So like this fulcrum, when it's in between these, we can shift this fulcrum so that it's way over here, which if we put the fulcrum there, that means that that effort arm is going to be really small compared to that effort, or to that resistance arm, which means that the IMA becomes less than 1, okay? Becomes something really small. Now, that's not a good thing for a force advantage, because if you remember, force advantages always happen when we have IMAs greater than 1. So this is more one of those ones where the distance that we move here is going to be very little. It's going to be a big distance that we're going to move here. So really, this is going to give us an advantage distance. So we're going to be able to move a little bit here, and we're going to lift something really high here. So that could be a setup that could be good for us using that lever. Now the other option is we could slide this more this direction. Okay, so when we slide it closer to here, now all of a sudden this becomes small, this becomes big. That's when the IMA is definitely bigger than 1, and this is an advantage force. So when we look at the setup of that lever, we're going to slide it back and forth, and we're going to be able to see whether that IMA is going to give us a distance advantage or a force advantage. Now this is technically a lever that we call a first class lever. So a lot of first class levers in this world, we can kind of use those all the time. It's typically when we're trying to pry something, so like hammers. If you use the claw part of it, it's going to be more like a first-class lever. When we start to set up the other classes of levers, though, so this is where there's a second-class lever. This is where we're now putting a fulcrum on the end. So now the fulcrum goes on the end, and we're going to put our beam out here, and we're going to then put the load in the middle, and we're going to lift up on this one. So this is one where we're now lifting up the same direction as the load is going, okay? Where if you look back to that first class lever, we were pushing down, but the load was going up. So sometimes there's an advantage in changing the direction. It helps us because maybe our applied force now gets to be our weight. So like our weight's going here, more like a teeter-totter, so we can lift something up. But in this case, we're lifting up, so our applied force is going to go up. Our F of G that we're lifting is going up. So this is more like a wheelbarrow. So like if we put a tire here instead and we're lifting it, this is our wheelbarrow example. Now if I go into my third class lever, a third class lever now is again similar to this. The fulcrum is going to be on the end. So again, put a fulcrum on the end. The difference now is I'm going to put my load way out here on this end, and I'm going to apply my force on the inside. So here's my applied force, and here's my force of gravity that I'm lifting. Again, both of them going in the same direction. The difference here is I'm going to move very little, okay? This is going to move really big. So really when we look at this, we're seeing this as an advantage to the distance, not an advantage to the force. Okay, second class levers, always an advantage to the force. So that distance from the pivots are greater. This one, the distance from the pivot is smaller. So this one's always going to give us a distance advantage. This one's always going to give us a force advantage. Now, this kind of stuff happens all the time. This is actually like all of our anatomy, all of our muscle structure. If you think about your elbow being your joint, the muscle that's going to contract that is put out here, even though your hand is out here. So if you hold something in your hand and you go to flex, you're moving a little bit to move that a lot. That's why this muscle has to be so big, is because it has to if we want to lift those big weights. So again, third class lever, we see that a lot. It's anything that has a pivot back here. You keep your hands in here and you're moving something way out here on the end. A lot of our sports equipment use third class levers as well. All right, so now once we've talked a little bit about those levers, let's extend this out into the other simple machines. By the way, we didn't look at the efficiency here. So like if we think about where friction plays a role in any of these, it's really at that pivot point. So there's a really low amount of friction. So these are fairly high in their efficiency. Okay, because the friction is low. Now, if we extend this out again, think about that first class lever, and I'm going to put my pivot point right here, and then I'm going to take and I'm going to make a very small little effort resistance arm or a load arm, and I'm going to make a very big effort arm. But I'm going to do this. I'm going to take the end of this and I'm going to pivot this around, to make a circle. And then I'm going to make a circle out of this one as well. So like when I turn this around, this is going to be what we call the wheel. This is going to also turn around. That's going to be the axle. And so this is a wheel and axle setup. So IMAs of a wheel and axle are based on radiuses. But the radius is really like the lever arms of our first class lever. So again, it's the radius of the wheel, or I should say the big radius, divided by the small radius when we are moving the wheel. So if we rotate the wheel, then we're going to move a big radius around. There's going to be a small radius here. That'll give us an IMA that'll give us a force advantage. Now, if we do this the other way, okay, so typically we'd see something like this where we're going to attach a rope to this. We're going to lift a bucket up. So this is like on a crank for a well or something, where we're going to turn the wheel and we're going to lift it up. A boat lift. A boat lift is a good example of this as well. But what happens if we reverse this? So what happens if we go with the IMA the other way, where we take the axle and the wheel? So in other words, I'm going to reverse this. So now I'm going to do my wheel, I'm going to attach my weight to the wheel, and I'm going to turn the axle. So as I turn the axle, I only have to move a little distance, but I end up moving a big distance here. This is the way we kind of set up like things like cars. So the advantage, though, is not in a force advantage, it's an advantage in distance. Okay? And so that's kind of the way we set up our wheel and axle. Now the other one that's kind of similar to this, it would be a pulley. Okay, our pulleys are actually different. If we think of it this way, I'm going to take a single pulley, I'm going to attach it to the ceiling, and I'm going to loop a rope around to my box that I'm going to lift. In this one, like with just a single pulley, I'm really not getting any kind of an advantage, because think about the distance that I'm going to have to lift this up. So like if I'm going to move this up this distance, so this is going to be my output distance, I'm going to have to pull that same length of rope in order for it to move, which means that if I pull the same distances, that means my forces have to be the same, which really doesn't tell me that I'm doing anything except changing the direction in which I'm pulling. So in other words, again, maybe I'm using my weight to lift this up and a little bit of gravity to help me. So it seems like it's easier when I'm using a single pulley. When pulleys really start to come into play, it's when we start to use more than one pulley. So I've got a fixed pulley I'm going to put at the top. I'm going to take another pulley and attach it to my block that I want to lift up. Okay, and I'm going to take this string now, I'm going to tie it off to my pulley, I'm going to loop it around here and then loop it back around here, and I'm going to pull this direction. So I'm still pulling down just like I was in this pulley, but now each of these two ropes is going to have to be shortened. So in other words, if I want to go from here to here as my distance out, I'm going to have to take this segment of rope and this segment of rope and switch it. So in other words, I'm going to need like twice the distance in order for that to happen. So now all of a sudden I'm at an advantage where I know this is a force advantage. Because if this becomes big and this is small, then I know that I have a force advantage. Okay, so my IMA is now bigger than 1, which means that I'm going to be able to multiply how much force I can lift. Okay, so in other words, I'm going to go in here and I'm going to say my IMA is now equal to the number of strands of rope connected to this box. So this is an IMA of 2 because I had 2 ropes connected. Now we can do something like an IMA of more than that if I wanted to draw another pulley here. So I'm going to put a pulley here, and let's put a box down here. Let's give another pulley here, but we're going to make a double pulley. Let's make another double pulley here. Switch colors just so it's easier to see what's going on. So I'm going to take my strand of rope, I'm going to tie it off, I'm going to go around that pulley, I'm going to go around this pulley. I'm going to go around that pulley, and now I'm going to pull down this way. So now I look at this and I say, well, how many strands do I have connected? 1, 2, 3, 4. So really this is an IMA that's equal to 4. So I can lift 4 times as much of this. So if I know that I'm going to pull, so this is going to be my applied force. So maybe my applied force is going to be 5 newtons. I'm going to pull with 5 newtons. That means that that IMA of 4 lets me pull 4 times as much weight. So really I can do 5 times the IMA, so I can get 20 newtons is what I can lift with this setup. Okay, so that's the way that I can look at that. I'm going to have a couple of problems for you to kind of walk through, so you'll be posting the solutions to those problems. I also have a little video that I think will be kind of a good one for you to watch, and it kind of goes through the pulley setup a little bit more, but hopefully this helps you to better understand our simple machines.